Okay, I'm back now, for real. This fits the page about as well as it's gonna. Yeah, alright. So how do you find the inverse of a log function? Well, you flip the variables like always. Turn your y variable into x, turn your x variable into y. Then you want to isolate the log, so you'd add 3 and divide by 2. Once the log is isolated, you convert to exponential, and then you solve for y. If you had an exponential that you had to find the inverse of, you do the same thing. We saw that in the classwork, but it looks like no example made it into the homework. But you would do the same thing where 150, yeah. You would still isolate the exponential, this bit. So you'd want to subtract 5, divide by 3. Then once you've done that, you would convert to logarithmic notation. And then when you're in log form, you'd solve for the y and get some answer. But I'm going to stick to the homework, stick to the 2 logs. And like I said, first things first is switch the variables. Second thing second is isolate this log by adding 3 to both sides to get rid of it and then dividing by 2. So if this is x and this is y, then we're going to pretty quickly end up with an x plus 3. And then rather than divide by 2, y'all should know by now, I prefer my coefficients. Just multiply by 1/2 instead. This is now equal to the isolated log, base 3, 4 minus 2x. So I can now convert this to exponential notation. Again, we keep the base. We raise it to the power of what the log was equal to. And then we set that equal to what you were taking the log of before. So 4 minus 2. I said 4 minus 2x. Most of you knew I meant y. So now you got to isolate y. So you're just going to, subtract 4 and then divide by -2. So that brings us to 3 to the 1/2 x plus 3 minus 4 equals -2y. Then you're going to multiply through by -1/2 on everything, and that'll bring you to your final answer. So when you multiply by -1/2, it doesn't touch the base, it doesn't touch the exponent, it doesn't change anything. It just becomes a coefficient on an exponential whose base is 3, whose power is 1/2, x plus 3. So nothing about that exponential changes, except it picks up a coefficient of -1/2. Now when it distributes onto the 4, that'll change it into a plus 2. And then we'll be equal to y. Although instead of y, at this point we'll say inverse function. So there's your inverse function. So after doing all that work, you'll rewrite it into the box. But I won't. I'll be lazy. And I'll just stick it in there. There you go. There's your inverse function. Now they're asking you to find the domain. So you got 2 choices. You can either find the domain of this function directly. It's an exponential function, so ideally you would know that the domain of an exponential is all reals, because the graph of an exponential has a horizontal asymptote, which would be up here at 2, would go up 2. Then with a base of 3, it would be exponential growth, but with an a value of that's negative, our little growth function would turn into a reflected growth model that decreases. This is still called a growth model, don't forget. When we talk about exponential growth and decay, it's really based on the base only. So a reflection from an a value doesn't turn me from growth into decay. It just turns me into a growth model that decreases. Don't forget that. Anyway, long story short, guess what my domain is? It's all reals. Because exponentials always have a domain of all reals. I said there were 2 ways to think about this. The other way to think about it is to remember that the domain of the inverse is the range of the original. And so you might remember that log functions have a range of all real numbers. They have one end that runs down, down, down to negative infinity along an asymptote. The other end goes up, up, up to positive infinity just very slowly. But the range is all reals. So however you slice it, this guy should have a domain of all reals. For the range, I kind of gave it away already, didn't I? Because I said our asymptote is given by the vertical shift. So we already know that our asymptote's at y equals 2, which seems to imply that our range is going to be from negative infinity up to 2. And it is. So that's our range. And for the asymptote, I kind of gave that away too. For an exponential function, it's going to be a horizontal asymptote. It's going to occur at y equals basically whatever this vertical shift is. So there, that one's done. The next one should be similar. So let's do it. What am I doing? I'm tired. Why am I doing this? Boink. Boink. There. Extra workspace. Alright. I'm gonna work in dark red. So what are we doing? Same thing as before. We said this y value is now an x value. We said this x value is now a y value. And we said that we want to isolate this log. That means get rid of the 7 by subtracting it. It does also mean get rid of this negative by multiplying through by a negative. So we're going to end up with x minus 7. Multiplied by a negative, so it'll just be sort of negative parentheses x minus 7, and then that's going to equal our log of 1/3 y plus 2. Alright, well now that the log is isolated, we're ready to convert, so we'll just take our 1/2, raise it to the power of negative x minus 7, in parentheses, set that equal to 1/3 y plus 2. A couple things are going to happen. I am going to resolve this negative and go ahead and just let my base become 2. Negative means take the reciprocal after all. So it's just 2 now to the x minus 7. Then this plus 2 I got to get rid of, so I'm subtracting 2. And that'll give me 1/3 y, which of course I'll clean up the 1/3 by multiplying by 3. Don't forget that the 3 will apply to both terms. I've got 2 terms here because of the minus sign, so you have to distribute it there. On this side everything cancels nicely, so I now have f inverse. Over here, again, the 3 does not multiply any part of this. It just becomes a coefficient on the exponential term to the x minus 7. The 2, however, does become a 6. But there you go. You've got your function now, so we'll be lazy. Lock all that. Now I can grab this. I guess I could have done that before. Alright, just want to be lazy. Here's my function. That one right there. So what's its domain? Same deal. It's exponential, so you can very mindlessly just say that its domain is all reals. You know that the domain of every exponential is all reals. Furthermore, you know that the range is always going to be either the horizontal asymptote up to infinity, or it's going to be negative infinity up to the horizontal asymptote. That is literally the only 2 choices. So let's imagine sketching this. We know that our parent function would have its asymptote at 0, so this vertical shift down 6 is going to put our asymptote down here at negative 6. We know that with a base of 2, we represent a growth model. The 7 just wants to push me to the right. That doesn't change much. Fine, I'll move to the right. and the 3 just wants to stretch me vertically by a factor of 3, fine. That just means I grow a little bit more quickly. My graph is still basically just this, which means we're going to be of the form horizontal asymptote to infinity. So not this one. And we know that the horizontal asymptote is at -6, so that's our range, -6 to infinity. Then they want to know the asymptote. Well, duh. We just said it's the horizontal asymptote that occurs at y equals -6. And work area, be damned, I did my work over here. That's it. Questions? What could you do if you had questions? You could email me, but I'm honestly not going to check it, I don't think. Better see me in the morning on Monday. Alright, so we're down to day 5 now. It's only been 11 minutes, so we'll do this all in one video. Oh, there's no homework. Except, wait, there is. Better pause the video and go get that homework. Okay, so I'm back. So I looked, and I don't have it. So the day 5 classwork we've already done. I think we talked it to death in class. I don't have the day 5 homework. Ms. Lee is the one who submitted the packets for copying, and I never got a copy, so I'm gonna do the best I can. I just went and I found some other problems. So sorry if you wanted feedback on the actual homework problems, I just can't give it to you. But I'll do some more problems if what you needed was practice. So again, pause the video if you want, and you can kind of work through this problem yourself and then check and see if you agree with me. The next one I'll do is this one here with a base of 1/5. And then the third one we'll do, which is probably the most representative, is this one. I think the quiz is probably going to have a transformation in every possible location. Like there'll be an A, there'll be a C even, there'll be an H, there'll be a K. So this third one is probably going to be the best bet. But let's start with 5. Like we said, the most important thing here for graphing is choosing X values that like make sense. Okay. So with a base of 4, you know that the values that make sense are going to be, well, think about it. Where do I have room to write? You know, log base 4 of 4 is certainly really easy to evaluate. It's 1. So 4 would be a wonderful choice. And who else? I mean, log base 4 of 16 sounds good in theory. Certainly easy to evaluate. It's 2. But think about 16. 16 is a big number. And for this problem, you know, X would have to be what to give us 16? It would actually have to be 16 plus 6, which is 22. 22 is not going to be on most grids, right? So we got to start going the other way in terms of powers of 4. We did 4 to the 1. We did 4 to the 2. No, we got to go the other way. Don't forget there's always 4 to the 0. So log base 4 to the 0 is 1. So log base 4 of 1 is a good choice. It would give us 0. And then, of course, log base 4, if you had 4 to the -1, then you could evaluate at 1/4. So, oopsies. When I said choose your x's wisely, this is what I meant. I meant that you're going to want to be evaluating the logs at values of x that give you -1, 0, and 1. And so that means evaluating at 1/4, 1, and 4. But that really means letting x equal something else entirely. So to get 4, we would evaluate at 10. And to get 1, we'd evaluate at 7. And to get 1/4, we'd evaluate at 6 and 1/4. So, you know, doing that math as a mixed number is easy, but I hate mixed numbers, so make sure you convert it to an improper fraction. So 6 times 4 is 24, plus 1 is 25/4. But those are going to be the 3 values where I would evaluate. Don't forget, you also can be finding your asymptote. For a log function, your asymptote will be vertical. And it'll occur at x equals whatever the 0 of your argument is. So for us, that's 6. So we've got some good information already. We know that we've got this asymptote at 6. We know that our graph is going to live to the right of that because there's no reflections anywhere. So we could say already that our domain is 6 to infinity. We know that our range is always all reals. To find the X Intercept, we are going to have one. The X Intercept is what we'll get when we set the Y value to 0. So we won't do that now. That's likely to come out ugly. So we'll do that later. And the Y Intercept, we can see that this problem again is going to have none. Anyway, let's evaluate. At 10, what's about to happen? Remember, we're going to just take 10, plug it in. When you plug in 10, of course, 10 minus 6 makes 4. Then you can just evaluate the log, because remember, we chose it wisely to come out cleanly. So the log base 4 of 4 is just 1. So you're now looking at half of 1 minus 5. So that's 1 half minus 5. Almost got that wrong. Jeez. So 1 half minus 5 would be what? Negative 4.5. AKA negative 9 halves. And so there's your first order pair. We could plot that to start thinking about our graph. For the next order pair, this time we're plugging in 7. So you plug in 7. 7 minus 6, of course, becomes 1. The log base 4 of 1 is 0. Remember, we planned this all out ahead of time. We already knew this was going to be 0. So you now have a half times 0 minus 5, which is 0 minus 5, which is negative 5. So there's your next order pair. And then finally, if you plug in the 25/4, this sounds like it's about to be hard work, but again, don't forget, we planned this ahead of time. We picked 25/4 because we knew that 25/4 minus 6 is what would give us 1/4. And then the log base 4 of 1/4 would be negative 1. So we've got a half times negative 1 minus 5. That's negative a half minus 5. That's negative 5.5, which is negative 11 halves. So now we can plot these points. The red one will go to 10. Negative 9 halves is 4.5. So that's a little bit off the grid. I didn't really plan the grid out very well, obviously. They're all going to be off the grid. So let's just play that game where we pretend that the axis was actually up here. Oh, that changes so much. Okay, this is fine. Alright. Negative 2, that's going to be. Why are you still white? Black. Negative 2, negative 4, negative 6. Hopefully that buys me enough real estate. That's 2. Okay, geez. So this point should actually be at 4.5, we said. So go to 10, go to 4.5. That's actually here, because 5 is right here. Yeah, so 4.5 is right there. Great. Now in blue, we're going to go to 7. So 7 is here, and we're down to 5, which is there. This doesn't feel so good. And then the purple one, we're going to 25/4. That's 6 1/4. So we're here, and we're down to negative 5.5. So we're here. Yeah, okay, that's fine. Whatever. So then our graph would be coming up, 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 this vertical asymptote, and then it wants to hit the purple, hit the blue. It's going to curve, basically flatten out, but it's not really flat. It's still increasing, but it's going to go like that. So this makes me really not want to find our X Intercept, because it's going to be way the heck out there at like, geez, probably 1,000 or something. But let's do the math just to make sure you can, I guess. Hopefully you guys are clear. I mean, the most important part is, can you choose your x's wisely? Once you've got your x's, can you evaluate the log to get your y values, and then can you plot them? This graph is fine. As far as the X Intercept, that's just going to be an algebra problem, so let's do it quickly. I'll hold on to that equation, scroll us down. Now, that moves the equation too, of course. Alright, well, we said to find the X Intercept. You know that at X Intercepts your Y value is 0. So you're setting this whole function equal to 0, and you'll just solve algebraically. So if this thing equals 0, right away you're adding 5 and then multiplying by 2. So you'll have log base 4 of x minus 6 equals 5 times 2, so 10. And here's where you can see that our answer becomes huge, because we're going to convert to exponential. So we get 4 to the power of 10. Like, that's a huge number. And it equals x minus 6. And then you're adding 6. So 4 to the 10 plus 6 is our x-intercept. For the curious, 4 to the 10 plus 6 is a monstrously large, like 4, damn it, 4 to the 10 is how much? You know, it's pretty big. Plus 6. Ooh, that's times. Plus 6. Alright, what did I estimate it as? Like 1,000? Yeah, it's 1,000,000. I was gonna say 1,000,000, and then I was like, no, let me, anyway. It's literally 1,000,000. So, whatever, great. As long as you understand the algebra, you're fine. You should be able to give me the answer of 4 to the 10 plus 6. You should be able to give me the answer of 4 to the 10 plus 6. I wouldn't ask you to evaluate it, but I would expect you to be able to give it to me. So if I were to ask for the x-intercept, even if it was unruly to the point of being in the millions, you should still be able to find it, even without a graphing calculator, because you can give me the expression 4 to the power of 10 plus 6 is my x-coordinate, comma 0. As dumb as that looks, you could do it. Turn this thing back off. Alright, I'm back. Alright, that was one example. Here's another. The big change here is your base is now a fraction, but guess what? That's not actually a big change, because you still want to choose your x's wisely, because you know that what you're going to want to do is evaluate here at the base, the 1/5 to the 1, at the base, the 1/5 to 0, and at the 1/5 to the 1. Negative 1, sorry. So in this case, the negative 1 is easier, because you take the reciprocal of the base, you get 5, which is a whole number. So you know that you'd want to evaluate at 6. That's sort of the easy one. We'll figure out our y value. 1/5 to the 0 is easy as well. It's 1. And so you'd let x be 2. And then here's where you actually get your fraction, your 1/5. So you'd want x to be 1 and 1/5, aka 6/5. But there's your well-chosen x values. I hope that is starting to click for people. So now we do the math. And again, plugging in 6/5 leaves us with 1/5. So the log base 1/5 of 1/5 is 1. And 1 plus 2 is 3. When you plug in 2, you're now doing log base 1/5 of 1, which is, that whole thing is 0. And 0 plus 2 is 2. And then you plug in 6. And you get 5. So log base 1/5 of 5 is negative 1, and negative 1 plus 2 is 1. So it looks like all these points will fit in just fine. But don't forget your asymptote. We know that our asymptote is a vertical asymptote that occurs when x equals 1. So I can plot that. It's here. I can plot my points. 6/5 is what, 1 and 1/5, so it's just barely to the right of the asymptote, and it will have us up at 3. And then 2 is a point, so that's here, and 6 1 is a point, which is here. Now, could we find another point? I don't think so. I think we're going to be off grid. Our other point would come from where? 1/5 to the -2. So that's 25. So we'd have to go all the way out to 26 to get what? -2 plus 2, which is 0. Oh, well, the happy accident, that's our X Intercept. 26, 0. But no, we're not going to get all the way out to 26. It's too far off our grid, which is fine. We can just sketch our graph. We are coming down the asymptote. You can see that. And you knew that because our base was less than 1. When your base is less than 1, you get a decreasing logarithmic function. So down we go. At least by evaluating at 26, we know that we should never see this graph dip below the x-axis. So control your descent. Make sure you leave the window still above the x-axis, because our point of intersection with the x-axis isn't until way the heck further out. Little tip for you. Are we done here? What's our domain? It's going to be everything to the right of our asymptote, which is 1. Our range is all reals as always. Our y-intercept again is that we don't have one. That's it. There's another log function graphed. And so here's one more. I feel like I should probably give you one that has an asymptote here or something, but goes this way. There should be a reflection, right? So that we do get both an x and a y. So let's modify this. I'm sorry if anyone already worked on it. 1,000 pardons. But it's in our best interest for sure. So why don't we go ahead and let this be what? Negative x. If it's -4, we go to the right. I'm sure I would distribute this in. So let's do -x plus 4. Now that negative is going to have the effect of reflecting us, blah, blah, blah. But let's do this one. I'm going to need a new grid though. So I should pause the video probably and go get a better looking grid. See you in a minute. Okay, I'm back. But while I was gone, I learned that it turns out I'd really like... Why is that huge? Okay, it's not really huge. I'd really like this not to be +4. I'd really like this not to be +3. I'd really like this to be +5. And this to be +1. Okay, I'm not going to change this again, I promise. But from here, this is a good one, okay? This is going to show you all the stuff you need to know. So, let's do it. Alright, y'all know the drill. We want to intelligently choose y values, which means we want to be evaluating at powers of 2. And specifically, we want to be evaluating at 2 to the -1, 2 to the 0, and 2 to the 1. So let's start with the whole numbers. 2 to the 1 is 2. So what's going to make this 2? If for some reason you can't do it in your head, then there's no shame in doing it off to the side on scrap paper that you don't show me. So maybe there's a little bit of shame because you're hiding it from me. But holy cow, if that's a 2, then what are we doing? You're going to subtract 5. What have I done? Maybe, I don't know. Oh, okay, geez, okay, sorry, I'm having a brain fart. Anyway, you subtract 5, you get -x equals -3, so you get x equals 3. But of course, I mean, that's obvious, right? -3 plus 5 is 2. You should be able to do this in your head. Not always, but for this one you probably should. So certainly 3 is a well-chosen x value because it gives us 2, and log base 2 of 2 is very easy to evaluate. Next, 2 to the 0 is 1. So you'd want to add -4 to 5 to get 1. So you'd let x be 4. That's another well-chosen one. And then 2 to the -1 is a half. To get a half, you'd want x to be 4.5, aka 9/2. So there's your well-chosen x's. Now we're evaluating. Again, 9/2 was purposefully chosen to give us 1/2, and then log base 2 of 1/2 is -1. So then 1/2 times -1 is -1/2, plus 1 is positive 1/2. Again, do the math out. If you can't do it in your head, just do it out. Next, we plug in 4. And 4 gives us log base 2 of 1, which is 0, times 1/2 is 0, plus 1 is 1. And then plugging in 3 gives log base 2 of 2, which is 1, which gives me 1/2. 1/2 plus 1 is 3/2. So there's your 3 ordered pairs. Don't forget, you're going to always want to graph your asymptote too. It does a lot of work shaping it. Now the 0 here is +5. So it's a vertical asymptote at x equals +5. +5 being right here. And then you can see with all of our x values being less than 5, you know that your graph lives to the left of that. So your domain therefore is -infinity to 5 instead of the other way around like it has been. We've seen graphs that all lived to the right of their asymptote, but because this one's reflected, it lives to the left of its asymptote. Our ranges are reals as always. I don't know what the heck that was. Plot your points. The blue one is at 4.5. So right here, and 1/2 is right here. 4,1 is here, and 3,1.5 is here. So those are points. And so you can see that this time when we go to connect these dots, we're going to come through all 3. We are going to hit the x-axis somewhere between there and there, and then just be asymptotic. Then here, what's my growth? Am I going to go wee like that, or is it going to be more controlled like wee? Well, finding the y-intercept is a good idea. We got to find it anyway, so it's a good idea to maybe just find it. Again, just one more time. The other thing you could do, of course, is go one more step. We could do 2 to the 2, which is 4. We'll get 4 when x is 1. So letting x be 1, we get log base 2 of 2. Half of 2 is 1. 1 plus 1 is 2. So you know that the point 1, 2 is on your grid. So that certainly helps shape sort of the steepness of our graph. It also lets me know that my y-intercept will be a little bit greater than 2. How do I get rid of those ugly branches I drew? Connected to everything. Ugh, annoying. Delete. What are you connected to? Nothing? Good. Get out of here. Alright. So finding that 4th point is useful. It definitely helps us sketch this a little bit better. So off I go through there, and I'm going to continue to rise slowly, slowly, slowly. But there you go. There's your graph. The X Intercept. The y-intercept's easier. Let's find that first. To find the y-intercept, you know that x is 0 there. So you're plugging 0 into this function. So you end up with 1/2 of the log base 2 of 5 plus 1. Okay, some of that went behind my face. Not really, kind of did. There you go. Now you can see the whole thing. That's it. You can't clean that up, so just don't. If I ask you for this value on the quiz, feel free to just say that the y-intercept is 0, comma, and then the y value is 1/2 of the log base 2 of 5 plus 1. Literally just give me the whole expression. And what's the value of that? It must be something a little bigger than 2. It's irrelevant. You don't need that point, so just give me the approximation. Now, to find the x-intercept, we said that we would need to take this function and set the whole thing equal to 0 and solve. So we'll do that. A little further down. So if I set the whole thing equal to 0, then I'm going to want to isolate my log. This feels a little familiar. That means subtracting 1 and then just doubling. So you'll end up with log base 2 of a negative x plus 5. It'll equal what? Negative 1 and then doubled. So negative 2. So you'll go 2 to the negative 2 equals negative x plus 5. 2 to the negative 2 is 1 over 2 squared, so 1/4. Then you'll subtract 5 from that. That'll equal negative x. 5 is 20 fourths. So you're looking at negative 19 fourths, which equals negative x. So that means x is positive 19 fourths. Which, let's not forget, is just 1/4 less than 5. So this thing is 4.75. Which should make sense when we go back to our grid. At this point right here is 4.75. And because it is. So the X Intercept is, if you want to give me 4.75, you can, of course. I'm going to stick with 19 fourths, comma 0. That's going to do it for graphing. We choose our x's wisely. We find the y's that go with it. We plot the asymptote. We plot our points. If you want to find a fourth point, go ahead and do it so that you can get your curvature a little more squared away. But that's it. So let's wrap this up. So this is video 3. And I think I did promise y'all that that bonus sheet that I gave you, the extra practice that you guys had on the block schedule day, I said I'd do a video on this thing, so sure, I'll do that too. You'll have 4 daggone videos. So that's coming right now. See ya.